Topic for today is causal abstraction. This video is going to be a sort of intro video, generally trying to go over what that means and maybe a few examples. So, causal abstraction. Basic idea, we have some causal model, a DAG, think Perl, that sort of thing, and we're going to abstract it into a new causal model. So like maybe we bucket together a bunch of nodes, like so, and we throw out some information from some of them, and then we map them over to some new nodes in a new model, and we find that the new model has a causal structure in and of itself. So what does that mean? How do we do it? That sort of thing. So, examples. Thermostat. Pretty simple. At the concrete level, we turn a knob, and then the thermostat is going to measure the temperature in the room and the setting on the knob in order to determine how much heat to crank out. And then it's going to do that again and again and again. It's going to keep doing that for a while. So, on the concrete level, we have this sort of back and forth causal diagram over time. On an abstract level, I turn the knob and the temperature changes. So we're sort of going from this causal model to that causal model somehow, and they both seem to sort of work in the sense that we can use them in our day-to-day lives, right? Another example, a little more complicated, fluids. So at the classical concrete level, we have a bunch of particles. They each have some position and some momentum at each time, and they're going to have interactions which are reasonably localized. So for instance, particle 1 and particle 2 are nearby, so they're going to be exerting forces on each other, and that's going to determine where they move to in the next time step, both in terms of position and momentum. Whereas particle 4 is sort of over here by itself, it's further away, so it's not going to interact with these guys, and it's just going to determine its next state on its own. So we have these causal interactions, which are localized in space, and also obviously in time. We abstract that into a continuum model, in this case I'm just drawing boxes, where each cell has some momentum of particles and some average particle velocity. And then each cell interacts with its neighboring cells. So the average density and velocity within this cell at time 1 is going to be determined by the momentum and densities in its neighboring cells at the previous time. So each cell is interacting with its neighboring cells in the next time step. And again, both of these are models that in some sense work. We use them, right? They're causal models at different levels of abstraction, and they both work. One last example, circuits. So in this case, we have a concrete model where we have two voltages going into this little circuit here. It's an old TTL logic. It's a resistor, in case it's not obvious. And then we have some voltage coming out. So as a causal diagram, we'd say we have 2 voltages in, 1 voltage out. Okay. At the abstract level, we turn this into binary logic, right? So we're binarizing each of these voltages. We're just treating them as high or low, and then we're treating this circuit as a logic gate. Now the causal diagram looks exactly the same, but the nodes in that diagram are different. Rather than V1 and V2, these continuum voltages, we just have the binarized V1 and the binarized V2, so just high or low, and same with V out. And again, this works in practice, assuming we design our circuits properly. So, first big question that we're going to be thinking about over the course of this sequence is, when is an abstract causal model correct? So like we were saying, each of these examples, they work in practice, right? We use these models on a day-to-day basis, and they work great. What's up with that? I mean, I can't just make up some random abstract model and expect that it's going to magically work, right? So, the main idea here is it's about queries. Two main types of queries that you want to run on a causal model. First one is probabilistic, second one is counterfactual. So probabilistic queries would be something like here, what is P of B given A, or P of A given B, or just P of B, these sorts of things. A counterfactual query would be, well, what if we just forget about the original process that was generating A, and we come in and set A equal to some value, and then I want to say, well, what's the probability that B is 2 if I go and hard set A to 3? Or, alternative example, I go in and I hard set B to 2. And I want to know, well, what's the distribution of A given that? And when I say hard set, what I'm really saying is basically I cut this arrow, right? So this is typical Perl-style counterfactuals on DAGs. Now, we want to be able to run these sorts of queries on our abstract DAGs and get back the same answers that we would on our concrete DAGs. That's the main criterion for what makes an abstract causal model correct. We can see that if we go back through these examples. So first of all, the thermostat example. This is a really nice one, right? So first, obviously, if we do probabilistic queries, we can say, like, how is the temperature correlated with the position of the knob? When I turn the knob higher, or sorry, when the knob is turned higher, the temperature will be higher if we just observe during random times of the day, right? And that's completely consistent with this DAG over here. The more interesting part is the counterfactuals. So in this model, I can pose two types of counterfactuals. I can say, let's set the knob to, I don't know, 27C, and then observe what happens to the temperature, right? And obviously, if we hard set the knob to 27C, then the temperature is going to adjust. On the other hand, maybe I open all of the windows in my apartment and put a bunch of fans in there, so I have a lot of airflow and my heater just can't possibly keep up. I'm effectively hard setting the temperature to something. Maybe it's like 20C. Well, today it's a lot colder than that. Let's call it 5C. So I'm hard setting the temperature to 5C. I'm effectively cutting this arrow. What happens to the knob? Well, nothing. Obviously, the knob doesn't turn to adjust the temperature, for instance. If our abstract causal graph had an arrow going this way, then that would say, if I hard set the temperature, then the knob is going to adjust to match. That's clearly not what actually happens. Now, important point here is that both of those predictions match the predictions from our concrete DAG. In this concrete DAG, if I hard set the knob, that's going to influence the temperature at some long time. And conversely, if I do something to hard set all these temperatures, like I open all my windows, that's not going to make the knob turn. So this abstract DAG is making the same counterfactual predictions as the concrete DAG. And that's what we mean when we say that an abstract model is correct. We're saying that it matches the predictions of the concrete model, or the lower level model, on probabilistic and counterfactual queries. Okay? Now, it might not necessarily match on all possible queries. Certainly you're going to want to run all sorts of different queries in your abstract model. So, like if we have circuits, for instance, we might want to run any possible counterfactual and causal queries on this circuit. But if this is a big circuit and it's not very well designed, it may be that the signal-to-noise ratio dies out as we go from one end of the circuit to the other. And then we're not going to be able to correctly predict any possible voltages, any possible responses to the inputs, right? So there can be cases where it'll work for local queries, so to speak. Like if we look at some small part of it, we'll be able to guess the binarized output voltage from the binarized input voltages for this little chunk of the circuit. But if we have a bigger circuit, we might not be able to guess very accurately all the way from one end to the other. Now, if we design our circuits properly, then we can. We can design our circuits to enforce the abstraction. And that's part of what we're going to be talking about over the course of this sequence is what does it mean to enforce the abstraction? What are the things you have to do locally in order to enforce the abstraction globally? That sort of thing. that is it for this video. Make sure to leave feedback on if you like the format or not. Thanks.